Hello, this is video 30. In this video, we're going to talk about static friction. In the previous video, we just talked about kinetic friction. So kinetic friction was friction that occurred when the object was moving. Static friction occurs when the object is at rest. So it's the force that keeps the object from moving when you're trying to move the object. So it's a little bit more complicated here because we have an inequality in the definition. The static friction force is smaller or equal to the coefficient of static friction times the normal force. So mu s is that coefficient. It's just has the same purpose as the coefficient of kinetic friction. It indicates the roughness and how much friction there is going to be, but it's a different coefficient when your object is at rest. So friction is always parallel to the surface, and it opposes attempted motion. So again, the object is not moving. If the object starts moving, then you have to switch to kinetic friction. So this is a force, so the units are Newton, and it's a vector. So what we need to do is we need to understand, what does this inequality mean? So I have the next slide devoted to this. And I found a nice little picture here that really helps to explain it. So the idea here is that if you're trying to push the object and that static friction is opposing that attempted motion, that static friction force increases until it reaches its maximum value. So the more you push, the more the static friction is going to oppose that push. So you can see in picture A that there's a pushing force and the static friction equals that push. In picture B here, we're pushing harder, that force is bigger, so it means that the static force is bigger. But the static force is still equal to this push. And now in picture C, we're pushing harder. We're pushing as hard as we can though, because if we were to push any harder, the object would start moving. So that means that this value of the static friction force is the maximum possible value it can take, because any bigger, and it means that the object is moving and that we're dealing with kinetic friction. So when the static friction has reached its maximum value, it's still going to oppose whatever force is pushing it, but it's also going to equal the coefficient of static friction times the normal force. So you notice that in cases A and B, all we know about the static friction force is that it's equal to the push, and it's smaller to mu Sn, but that doesn't really help us because we don't have a value. So usually we just use the fact that it's equal to the pushing force and that it's equal to mu Sn only when it has reached its maximum value. And really don't forget that in all three cases, the object is not moving. So let's take a look here at a free body diagram for friction. So a car is parked on a hill, which is the correct free body diagram. So this is very similar to what we did in the previous video, but this time it's parked, it's at rest. So just like in the previous video, we eliminate E because there's no normal force. We eliminate D because the weight's not going straight down. We eliminate A because it doesn't show a friction force. And we eliminate B because the friction force has to be in the direction to oppose attempted motion. The car wants to slide down, so that friction force opposes it. So the only difference with the free body diagram with this and the previous video is that this friction force is going to be static friction instead of kinetic. The other two forces will still be the normal force and the weight. So let's take a look at one more example here. And we'll have some more examples that deal with static friction to work on the inequality in another video coming up. But this example here, again, it looks very similar to the one in the previous video, but this time it says how much force is needed to get the box moving. So the box is at rest. So what we need to do is we need to find that pushing force that will make the static friction force be its maximum value. And then we know that if the force is any greater than that the object will start moving. So what we're doing is we're looking at the definition of static friction force, but since it's the maximum value, we can use mu s times n, only because it's maximum value. So in general, you can use this equality when there's something in a problem that says you want to get it moving, or it's about to slip, something like that, that tells you it's the maximum value. Like in the previous video, that normal force is going to equal to mg. If we were to draw a free body diagram for this, you'd have the pushing force, F applied, you'd have the static friction force. Going left, you'd have the normal force upward and the weight going down. So we just need to plug in the values. This time you notice that the coefficient of static friction is 0.5 rather than 0.3. It's bigger. In general, it's harder to get an object moving than to keep it moving. So that coefficient of static friction is going to be greater than the coefficient of kinetic friction. And we're using g equals 10 just to simplify calculations. We get 500 newtons. So this is the maximum static friction force. In this case, the object will still be at rest. So in order to get the box moving, we need a force applied just greater than 500. If you push on this applet, you can try 500.0001 and it will get the box moving. So that's all for this video. So just to recap, when you're dealing with static friction, only use the equality that the static friction force equals mu times n when the object is on the verge of slipping. Otherwise, all you know is that the static friction force just opposes the pushing force.